If you click on this video, you're probably trying to understand next equation. So in this video, I'm going to be teaching about next equation. I'm going to be teaching about next equation. But before I do so, there are certain things you need to understand before you actually get the topic of next equation, and that's going to be on electrode potential. So you need to understand the meaning of electrode potential and how electrode potential is actually related to the electrochemical series before we get to next equation. So let's move to electrode potential. Electrode electrode potential. So it is difficult to get the electrode potential of a metal, but for us to get the electrode potential of a metal, we need to compare it to the electrode potential of hydrogen for us to get the electrode potential of the metal. And we consider the electrode potential of hydrogen to be 0.0 voltage. That's the electrode potential of hydrogen. So we have the electrode potential of different metals and they have different values. But what you just need to know is you need to know the trend. So let me write the electrochemical series. The electrochemical series. As you all know, the electrochemical series for electropositive metals, that's the electropositivity series, is potassium, sodium, calcium, magnesium, aluminum, zinc, iron, tin, iron, tin, can you see what I think, lead, then hydrogen, copper, hydrogen, copper, mercury, silver, then gold. So this is the electrochemical series for electropositive elements. So we all know that the reducing ability of of metal is decreasing across the strength. So potassium is a stronger metal than sodium, and sodium is a stronger metal than calcium. Calcium is a stronger metal than magnesium. Why? Because this has higher reducing ability than the one beneath it. So this is decreasing, reducing ability, decreasing, reducing ability. So that just shows that potassium is more electropositive than gold, and gold is the least electropositive in this string. So how does this relate to electrode potential? Okay. How does this relate to electrode potential? Well, you should know that the electrode potential for hydrogen is 0.00 voltage, considered to be zero. So for metals above hydrogen, their electrode potential is negative. So this is negative, this is negative, this is negative, this is negative. They have an absolute value, but you should know that any metal above hydrogen is negative. That's electrode potential, which is negative. While the ones below hydrogen, they have electrode potential, which is positive. Positive. That electrode potential which is positive. So that's to tell us that for 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 metal to be very strong and to have a good reducing ability, the electrode potential has to be negative or has to be lesser. And that's to show you that the lower the electrode potential, that means the higher the metal or the stronger the metal or the higher the electropositivity of the metal. So you can see from this trend that potassium is having a negative electrode potential, but it is stronger than sodium because it has a higher negative than sodium, a higher negative value or a lesser value than sodium. While gold here is having positive electrode potential. Why good is having positive electrode potential? That's to show you that it has a very, very low reducing ability, or it is a least electropositive metal, or a lesser electropositive metal compared to potassium. So the lower the electrode potential, the stronger the metal. Or you can say the higher the negative value of the electrode potential, the higher the metal. But just is that the lower the electrode potential, the stronger the metal. So that's that one, electrode potential. Now, the next thing you need to know is you need to know when a cell is spontaneous and when a cell is not spontaneous, and the kind of reaction that occurs in the anode and the cathode of a cell. So let's say we have potassium and we have gold in a cell. In a cell, for this cell to be spontaneous, potassium has to act as the anode because it's the higher electropositive element. So the higher electropositive element has to act as the anode, while the lower one has to act as the cathode. So we should also not forget that in an electrochemical cell, reduction occurs at the cathode while oxidation occurs at the anode. You can use this mnemonic. So in an electrochemical cell, the cathode reduction occurs in the cathode, while the anode oxidation occurs there. Oxidation occurs there. So if you know this, you know that anytime you are given an element in a cell and it asks us to find the electropotential or the EMF of the cell, you need to know that the more electropositive elements will act as the anode. That's where oxidation will occur. While the lesser electropositive elements will act as the cathode. That's where reduction will occur. So you need to know that. And for a spontaneous cell, this will be undergoing oxidation, this will be undergoing reduction. And you should know that oxidation is loss of electrons. That means electron will move from the anode to the cathode because oxidation is loss of electron. So electron will move from the anode to the cathode. With that information gathered, the next thing on board is how to find EMF of the cell. So finding the EMF of the cell, you can find the EMF of this. You can find the standard EMF of a cell or just the EMF. Finding the standard EMF of a cell is when we do it the redox way, that's reduction minus oxidation. But to find just the EMF of the cell, that's when we move to next equation. That's finding EMF of a non-standard cell. But to find the standard EMF of a cell, use the redox minus oxidation. So let's take a question so you can understand better. So this question says a cell is given by x x2 plus, then y3 plus y, and and x2 plus x2 plus giving x2 plus giving x is minus 2.34 voltage, y giving y3 plus is equal to plus 1.90 voltage. So if you are given a question like this, how do you solve it? So to solve questions like this, you don't need to have too much knowledge on different things. All you need to know is your knowledge of cell notation. So in cell notation, this one single vertical line means the boundary between the element and the mole, the element and the mole. While these two boundary lines just represent salt bridge. So, what is the meaning of all this that we see here? What is the meaning? If you look at X, the oxidation number changes from 1 to 2. And if you look at Y, the oxidation number changes from 3 to 1. So we can say here that oxidation is occurring here because oxidation is an increase in oxidation number. And we can say here that reduction is occurring here because reduction is a decrease in oxidation number. So X is actually oxidizing while Y is reducing. Now, then they gave us the equation that x2 plus giving x is minus 2.34 voltage and y giving y3 plus is plus 1.90 voltage. This is the EMF. The EMF. That's they give the electric potential for x and for y. And they're asking us to find the EMF. They're asking us to find the EMF for this standard EMF, by the way. So if you look at this cell notation, it is moving from 1 to 2, but in this equation, it is moving from 2 to 1. So we want it to move from 1 to 2. What do? We have to reverse the equation. So when we reverse the equation, we get when we reverse the equation, we get x, let's see the board, x giving x2 plus. And when you reverse the equation, the sign of our E will also change. So that will be plus 2.34 voltage. So we reversed it. If you also look at y is moving from 3 plus to 1. And if you look at the equation here, y is moving from 1 to 3 plus. But we want it to move from 3 plus to 1, not 1 to 3 plus, because that was in our cell notation. So what do? We also reverse this. So when we reverse it, then y3 plus, we get y3 plus giving y, then the electric potential, the EMF, will be minus because when you reverse it, the sign will change. That will be minus 1.90 voltage. So the next thing we need to do is to add up the EMF. Since we've gotten the EMF of this, I've gotten the EMF of this. The next thing we need to do is just to add up the EMF. So the standard EMF of this cell will then be plus 2.34 voltage plus minus 1.90 voltage. That will be 2.34 minus 1.90, and that will give us 2.34 and 0.34 minus 1.90. 0.34 minus 1.90. That will give us 0.44. That will give us 0.44 voltage. So that's how to solve questions. That's how to solve questions like that. Whenever they ask you to find the EMF of a cell, just look at the cell notation, look at what is going on here, and look at the information they give. Then restructure the information they gave to fit the cell notation and find your EMF, then add up. So I'll take another example so we can understand better. Let's look at this example. This is a Daniel cell. So they asked us to find the EMF of this cell. Then they give us the cell notation. This is the cell notation. Then they give us the EMF for copper, the EMF for zinc, and they said to find the standard EMF. So to find the standard EMF, I've told you, all you just need to do is just look at the information given here in the cell notation and restructure this equation in a way it's going to fit this. So let's look at it. If you look at zinc now, zinc is moving from 1 to 2, and copper is moving from 2 to 1. But if you look at your equation, copper is actually moving from 2 to 1. That means it's the same thing. So you just have to leave this one like this. But if you look at zinc, zinc is moving from 1 to 2. But here, it is moving from 2 plus 2 to 1. That means we need to reverse this equation in a way. Zinc is going to move from 1 to 2, not 2 to 1. So it's as easy as that. And let me show you another trick. If it tells you to find the EMF of a cell, they are not going to tell you use next equation or don't use next equation. It is your own responsibility to know when to use next equation or not. So for you to know when to use next equation or when to find the standard, you look at the concentration. If you look at this place, the concentration is 1 molar. The concentration is 1 molar here and 1 molar here. So since the concentration is same, that's to tell you that we don't have to use next equation. But if it is different, we use next equation. So I'm just showing you that we'll get back to next equation later. So let's look for the EM of this. Zinc is moving from plus 1 to plus 2. Yeah, it's moving from plus 2 to plus 1. So we need to reverse this. So when we reverse this, let's reverse that for zinc. That will be Zn giving Zn2 plus 2E minus. So when we reverse it, our EMF will also reverse in sign. So instead of having negative here, we have positive as positive 0.763 voltage. So there's another thing you need to know is when we reverse an equation, the EMF will also reverse in sign. But when we multiply by a factor, we don't multiply the EMF. Why? Because the EMF is an intensive property, and intensive property doesn't depend on mass. So when we multiply it by a factor, we don't multiply EMF. And another thing you should notice when you are solving questions like this, make sure the electron in the two equations are balanced or are the same. When they are not the same, you have to still multiply by a factor. Maybe if this one is having E and this one is having 2, just balance it. But just know that when you're multiplying, don't multiply the EMF. So now we've reversed that for zinc. We reversed that for zinc. So let's just add up. That will be our EMF will be 0.337 plus 0.763. And that will just give us 0.337 plus 0.763. That will be 1.1, 1.1, 1.1 voltage. So that's how to find the EMF of a cell whenever they give you this. So this is just finding standard EMF. Standard EMF is so straightforward. Just find your standard EMF and you're good. But next equation is quite complex as you need to know a formula. You need to know how to solve it. So you have to know a formula and some conditions for you to be able to solve next equation. So before I move into next equation, I want you to know the conditions at which we, we get standard electric potential. So to find the standard electric potential for a metal or for an element, there are three conditions. The temperature has to be the temperature has to yeah, the temperature has to be 25 degrees Celsius or 298 Kelvin. The temperature has to be this. The concentration has to be 1 molar. So the metal must be in contact with 1 molar of its own concentration. 1 molar of its own concentration. While the pressure Pressure has to be 1 atmosphere or 760 millimeter mercury. So this is the condition at which we find the standard electric potential of a metal. So let's move to next equation.